With regression, we had to use some intuition, theory, and common sense to figure out what controls needed to be added into our model. Otherwise, we knew we would get a causal effect that suffered from omitted variable bias. Thankfully though, there is another causal inference technique called instrumental variables analysis in our toolbox, that controls for confounding variables, without having to specify all of them like we had to do in regression. Let's take a look at it in the next lesson. Instrumental variables analysis is the third causal inference technique we will cover. Consider the familiar example, where we have a regression of y on x, with w representing omitted variables. And we want to figure out the causal impact of x on y. Let's take a look at 4 hypothetical scenarios to see if any one of them can address the omitted variable bias. The first scenario is when w is related to both x and y. This structure should look very familiar, since we covered it many times from earlier modules. This is precisely the case where we have omitted variable bias. We want to include w, if we have data on it, because by including w, we reduce bias due to its omission. Since we often don't know what w is, we don't like this scenario. Next, let's consider the case where w is unrelated to both x and y. In other words, w is not connected in any way to the model. Therefore, in this scenario, we don't have any omitted variable bias, and we like this regime because we don't have to do anything. W is unknown, and that's fine, since it has nothing to do with the model. Next, let's consider the case where w is related to x, but unrelated to y. This is what social science researchers would call a bad case of multicollinearity, and we don't like that. You can basically think of it like this. X carries all the information it needs to explain y. Therefore, w is redundant, since x is already included in the regression. We want to keep w omitted. And finally, let's consider the case where w is unrelated to x, but related to y. Here, there is no omitted variable bias since there is no correlation between w and x. If we have data on w, great, we should include it, since its inclusion will help us model and predict y better. But if we don't, that's okay, since including w won't reduce bias. In summary, we like 2 of the 4 scenarios we covered, and it turns out that instrumental variables analysis is going to help create one of these scenarios. It's at this time that we are fully prepared to discuss instrumental variables, and see how the graphical structure of an instrumental variables analysis fits in with one of the 2 ideal scenarios we covered earlier. Recall that we are trying to estimate the causal effect of x on y, but cannot just take the raw correlation as causal, because there are omitted variables. For simplicity, let's lump them all into w. An instrumental variable, or instrument for short, is a feature or a set of features, z, such that the following assumptions are met. First, the exogeneity assumption. Basically, what this assumption is saying is that there is no relationship between z and w. This is why we mark the link between z and w with a red mark. Second, the relevance assumption, also called the strong first stage assumption. What this means is that there is strong causal relationship between z and x. And that is why we have an arrow pointing from z to x. And finally, the exclusion restriction, which states that z affects the outcome variable, y, only through its effect on x, meaning that the instrument does not have a direct influence on y. If all of these requirements are met, z is a proper instrument. Tidying up our earlier graphic, we have this. This is how the instrumental variables analysis looks in graphical representation. The intuition of the instrumental variable z is that variation in z causes variation in x, without affecting the variation in w. How do we know this? Because of the exogeneity assumption. What this means is that we can calculate the portion of the variation in x that is exclusively caused by variation in z, and uncorrelated with w. We'll use the notation x' to denote the portion of x that is unaffiliated with w. To summarize, an instrumental variables analysis involves using an instrumental variable z, which is correlated with x, but uncorrelated with w. The effect of this is that we are able to break x into 2 parts, a part that is correlated with w, and a part that is not. By isolating the part that is not correlated with w, we get x', which we can use to calculate the pure causal effect of x on y, and not the effect of x on y that is confounded by w. So how do we do the instrumental variables analysis in practice? Before we do anything, it's important to note that the most crucial step of instrumental variables analysis is reasoning that the instrumental variable satisfies the 3 requirements: relevance, exogeneity, and exclusion restriction. Once that's done, we run what is called a 2-stage least squares regression, and it's called by this name because there's two stages of regressions we have to run. The first stage involves the regression of x on z. The interpretation? We want the portion of x that is solely explained by z. We called this x prime. Running the first stage regression can give us the predicted values of x, solely attributed to just z. This is the same of getting just the variation in x, attributed to variation in z. The second stage involves the regression of y on the x prime that we derived from the first stage. The interpretation? Well, the coefficient on x prime is the magnitude of the causal effect of x on y that we are looking for. This coefficient is also called the two-stage least squares estimator. Intuitively you can think of two-stage least squares regression as like crossing two bridges, the bridge from z to x, and the bridge from x to y. As we did before with other causal inference techniques, let's head right into a real-world example. Acemoglu, and colleagues who are authors of the paper, The Colonial Origins of Comparative Development, wanted to study the impact of institutions on economic performance. By institutions, they meant things like property rights. They wondered whether having property rights were major determinants of economic performance, and key factors in understanding the vast cross-country differences in wealth. As institutions were not randomly assigned to countries, they were wary of biased estimates. Their solution? Look to history for natural experiments. What the authors looked to was the history of European colonization. They noted that historically, in some colonies, European settlers faced very high death rates because of diseases for which they had no immunity. Where settler mortality was high, the Europeans did not settle, and the colony was governed by an authoritarian state with the strict purpose of maintaining control and extracting natural resources and slave labor. Where settler mortality was low, the Europeans raised their families and settled, and the colony was modeled after the home country, which meant that those settler colonies had representative institutions which promoted freedoms like property rights. The researchers theorized that those past institutions that were set up by colonists persisted into modern-day institutions, even after independence. Given these qualifications, the researchers used an instrumental variables analysis with the instrument being settler mortality, to address omitted variable bias. To show that settler mortality was a proper instrument, the authors made arguments for why the three assumptions were met. First, the relevance assumption. Does settler mortality meaningfully affect today's institutional quality of countries? The authors argued that places with lower settler mortality in the colonial era actually implied that those countries had higher property rights in the year 1995. Second, the exogeneity assumption. The authors argued that the fact that some parts of the world, hundreds of years ago had higher risk of disease, was unrelated to other factors that would affect GDP in the year 1995. And third, the exclusion restriction. The authors argued that settler mortality did not directly affect GDP in 1995. And that seems plausible, because GDP today probably doesn't depend directly on whether settlers were dying in the year 1700. What's more plausible is that settler mortality affected early institutions which persisted over hundreds of years. After explaining the legitimacy of the instrument, the researchers use a two-stage least squares regression to find the causal effect of institutions on economic development. Note that the authors use a variable called the average protection against expropriation risk as a proxy for institutional quality, and the GDP as a proxy for economic development. This is the results table from the two-stage least squares regression. In panel B, the bottom area of the table, we can see the results from the first stage regression. The main finding in panel B is that the coefficient on settler mortality is -0.61, indicating a negative relationship that we had intuited before when discussing whether the relevance assumption holds. In panel A, the top area of the table, we can see the results of the second stage regression. The main finding here is 0.94, the coefficient on average protection against expropriation risk. This number is an estimate of the true causal effect of institutional quality on GDP. Because it is positive and statistically significant, the authors conclude that there is indeed a true causal effect of property rights on economic development. And lastly, the researchers add a qualifier that none of the results matter if the assumptions in an instrumental variable analysis are not met. Before we move on from this study, I'll just quickly note that this paper is quite contentious. You will find that contention is a pretty common theme in studies using instrumental variables analysis, because two of the requirements for an instrument to be proper are impossible to prove, meaning that no matter how much data we have, we cannot prove them. These two requirements that are patently unverifiable are exogeneity and the exclusion restriction. The exogeneity assumption states that the instrument and confounding factors are not correlated. This one is impossible to test since confounding factors are never observable. This is why researchers will have to rely on good theories and argumentation to say that the exogeneity assumption holds. Then there is the exclusion-restriction assumption, which states that there is no direct causal pathway from the instrument to the outcome variable. This assumption is also impossible to test, since it involves seeing the true model structure of which we never get to see. To motivate the exclusion restriction, we also need to rely on theoretical foundations to think about all the possible relationships between the instrument and the outcome. If the instrument affects the outcome through any other channels than the treatment variable, then the instrumental is not valid. In summary, the bad news is that good instruments are hard to find, because they have to satisfy three assumptions, two of which are impossible to corroborate empirically. But here's the good news: a good instrument, if we can find it, allows us to estimate the causal effect of the treatment variable on the outcome variable, free of omitted variable bias, without having actual data on the omitted variables. If you want to learn more about instrumental variables analysis, these are the resources I recommend. These papers will give you many examples of different instruments, and reasons for why they are good instruments.